Welcome to Lecture 17, The Evolution of Low-Mass Stars, Part 1. In our last lecture, we discussed the interstellar medium and star formation out of giant molecular clouds, protostars, and the Hayashi track, which represents the protostellar movement on the HR diagram. So now that we've brought the protostar to the place of its birth on the main sequence, today we're going to start a multi-part series of lectures on the evolution of those stars. You know, what we think about stars as being sort of just things that sit out there and give off a lot of light, and certainly they do that. But despite the fact that our sun, for example, will sit on the main sequence for 10 billion years and look very similar for the vast majority of that time, there is stuff going on inside, and what that stuff is important to understanding what will eventually become of the sun. And certainly what will eventually become of the Earth as the sun impacts us. So today is our first step in that direction, understanding the evolution of low-mass stars, of which the sun is one. So let's dig in. So again, last time we discussed the formation of true stars from protostars and the birth of the star on the main sequence. But it turns out that stars don't live on the main sequence forever. And the reason is simple enough to understand because what defines a main sequence star is the nuclear reactions occurring in the core converting hydrogen to helium. So for low mass stars, which is what we've focused on thus far, particularly in the context of the sun, that series of dominant reactions is known as the proton-proton chain. And so again, I introduced that in the context of the sun, but that's true of all what we call low mass stars. And I'll say more about what I mean by low mass stars, but to sort of cut to the chase, it's any star less than about 8 solar masses. So for any star whose mass is less than 8 suns, we call that a low mass star for reasons that will become clear. But anyway, that's that's what makes a low mass star a star, right? Is the series of nuclear reactions happening in the core. So those reactions are converting hydrogen to helium. But eventually, you can only do that so long because you run out of hydrogen, right? Eventually, there's no more hydrogen to be had. And so when we talk about the evolution of stars, basically what we mean is what happens after that. Well, after this hydrogen in the core is all exhausted, what happens? And then what happens after that, and so on. So that's going to be the focus of today, and not just today, but the next few lectures are going to be related to the evolution of stars. So that's kind of where we're going. So it goes without saying, but I'm going to say it anyway. We only observe stars for almost a minuscule fraction of their lives, right? So I've told you several times, the sun, we expect to be on the main sequence for about 10 billion years, right? We live for maybe 100 years if we stick around longer than most. So, I'm talking to you today about the evolution of stars, but no one lives long enough to see stars evolve, right? So how can we talk about that? How can we understand or verify anything about our models of stellar evolution if we can't even see this happen? And an example or an analogy is just imagine you go to a football stadium, right? And you take 1 minute to observe all the people, right? What do you know about their whole life, about the human life cycle? And the answer is, you would sort of infer that humans spend their whole lives watching football. And for some people that's more true than others. But the point is that, looking at a very small part of something's life can tell you very little about the rest of the life. So how do we learn if human lifetimes are so much smaller than stellar lifetimes? And fortunately, the answer is that there's a whole lot of stuff out there in the universe to look at that are in different parts of their lives, right? And so to start understanding that, I want to point out that the nuclear reactions in hotter stars proceed at a faster rate. This is actually an extremely important point to understand. If you've taken chemistry, you very often run into the same fact that chemical reaction rates will depend upon the temperature of your system, for example. And very often, if you heat a system up, then you can make the rates go faster. So M-class stars can live for 500 billion years, which is much, much longer than the current age of the universe, which we think is around 13.7 billion years. O-class stars, on the other hand, which are the hottest stars, live only for 1 million years. So it's just 500,000 times longer for M-class stars than O-class stars. And then the sun is a G-class star that will live for about 10 billion years. So there's a huge variation in terms of lifetimes for these stars, and it all comes down to how quickly these reactions are occurring in the sun. Because as I have told you before, and as is represented schematically on this slide, O-class stars are actually much more massive than M-class stars, right? So in order for an O-class star to live, to sort of reach the end of its life, it's got to go through a lot more nuclear fuel, right? But it turns out that it's so much hotter that the reactions occur so much faster that it still burns out 500,000 times faster than an M-class star. So it's pretty remarkable. So how do we determine the main sequence lifetime of a star? I've told you that an M-class star can live for 500 billion years, and an O-class star can die out in only 1 million years. But how do we know that? So let's make an analogy to driving a car. Okay, so what would determine how quickly you would run out of gas in your car? And there are a couple of things to keep in mind, right? One is, how much gas do you have? What's the size of your tank? And the second is, how fuel efficient are you? At what rate are you burning that fuel? So M-class stars have much less fuel than do O-class stars. But they're also less luminous, right? A lot less luminous, which means that they're giving off much less energy every second. And so the upshot is that they're using their fuel at a much slower rate, okay? So they've got less, but they're using much, much less every second. So this is like the hybrid car in our analogy. O-class stars, in contrast, have a lot more fuel, but they're also absurdly more luminous, okay? So they use up their fuel at an outrageous rate, okay? So you've got these competing effects, more fuel in the bigger star, but also much faster burn rate. And so a priori, it's not obvious what's going to win out. But as I've told you, it turns out that the burn rate is so much faster in these hotter stars that on balance, they burn out much faster than do the low mass stars. So as I've suggested, though I haven't said it, haven't been too detailed about it yet, we can divide stars on the main sequence into two basic groups. And it's based on what happens to the star when it runs out of hydrogen. So as I said, when a star joins the main sequence, what defines it as a star on the main sequence is these nuclear reactions converting hydrogen to helium in the core. The main topic of today is, well, what happens as a star evolves? And the first step of that is, well, what happens at the end of that hydrogen fusion when all the hydrogen in the core is fused? And it turns out there are two different answers depending upon how massive the star is. For stars whose mass is greater than about 8 solar masses, one thing happens. And for stars less than 8 solar masses, something else happens. And so that's why we choose 8 solar masses to be the demarking line between high mass stars and low mass stars. It's not just because somebody sort of picked a random number. It's because that number of 8 solar masses just makes a difference as far as what happens in the evolution of that star as it leaves the main sequence. So O-class and B-class stars are high mass stars. Everything else is a low mass star. And that everything else is 97% of stars in the universe. So the vast majority of stars in the universe are low mass stars. That's why I'm starting off talking about low mass stars rather than just cutting to the chase with high mass stars. Certainly our sun is a low mass star. So you'll also notice that down here at the last part of the slide, I say that low mass stars are somewhere between 8 solar masses and 0.08 solar masses. If you're wondering why they can't be less than 0.08 solar masses, you may recall from the last lecture that if a star, or if a protostar has less than 8% of a solar mass, then it actually won't even be massive enough to become a star. So it will actually become a brown dwarf or a failed star, and it'll stick around as a brown dwarf for a while, but won't actually become a true star. And so we're going to kind of leave that to the side. But now the question is, okay, we're going to focus on these low mass stars and ask, well, what happens to these things when they finally reach the end of their main sequence lifetime? And before moving on, I want to highlight something that I think I pointed out before, but when we look at the main sequence, these high mass stars, these 8 solar mass and greater stars, are all up in the upper left-hand corner of the HR diagram. They're very blue stars, they're very hot, they're very massive, very luminous, but again, 97% of stars are low mass stars. And that comprises a very large range, all the way from B-class stars that can be 20,000 Kelvin at the surface down to, sort of very abundant M-class stars that are, as low as 2,500 Kelvin. So there's a big range of different stellar types within the low mass category that we're talking about today. So let's go back now to focus on a single star on the main sequence, a low mass star, and think about what happens as that star evolves. So all stars begin their lives with the chemical composition of the gas in the interstellar medium, right? As you remember from the last lecture, stars form out of the interstellar medium. That interstellar medium is 99% gas, 1% dust. Of that 99% gas, it's 90% hydrogen and about 10% helium by atom number, right? Or 75% by mass hydrogen and 25% by mass helium. And so I'm going to focus, we typically have been talking about atom number fractions, but actually in this slide I'm going to talk about mass fraction. So when the sun is formed, if you look at the percentage of the mass that's in hydrogen and helium as a function of the distance from the sun's core, it's all uniform, because the gas out of which the star was formed was all the same. It was about, again, 75% hydrogen, 25% helium by mass, and that's true whether you're in the core or if you're out at the surface. But over time, these fractions change, right? Because in the core, by definition, the sun, or this low mass star, is undergoing the proton-proton chain, right? So hydrogen is being fused to form helium, and so the result is that the fraction of helium in the core increases over time, goes up from 25% and grows. And so here, when the sun was formed, the distribution looked like this. The sun today, about 5 billion years into its lifetime, looks more like this. So in the core, it's actually a little over half helium, about 60% helium by mass, whereas out in the majority of the star, actually, certainly near the surface, it has the same percentages that it ever had, right? Because fusion is only happening in the core, and so the core reaches out to about 20% of the sun's radius, and so you can see it decreases the helium fraction until at about 20% of the sun's radius, it hits sort of the ambient value and continues out. But as the sun continues to age, the fraction of helium in the core will continue to increase. And in about 5 billion more years, when the sun is about 10 billion years old, eventually all of the hydrogen in the center will be exhausted. And that's what we're interested in today. What happens next? So at this point, the star is going to have two main layers, right? It's going to have a helium core in the center, and then it's going to have an envelope surrounding that core, which is going to consist of hydrogen and helium, just as it always did. So you've got these two main parts of the star. Now, to understand what's going to happen at this point, we need to back up and remember why the star was in equilibrium to begin with, right? It formed due to gravitational attraction within the giant molecular cloud, right? Gravity was always acting as an attractive force. It was always tending to collapse that star. The only thing that stopped that tendency towards collapse was the internal pressure of the star. And in the case of the sun and any other main sequence star, that internal pressure is generated by the light that's released from the nuclear fusion reactions. But when all of the hydrogen is gone from the core, those fusion processes stop. Energy is no longer being released in the core. And so what happens? The internal pressure vanishes. So now you have an unbalanced force, and gravity continues to start collapsing the star again. So it was balanced for 10 billion years in the case of the sun, but now all of a sudden that internal force that was balancing gravity vanishes. And so what happens is the gravity continues to collapse. And it collapses, and it collapses, and it continues to collapse until a new kind of pressure emerges that can resist that gravitational contraction. And the new pressure that eventually does emerge in the case of the sun and any other of these 97% of the universe's stars called low mass stars, it's known as the electron degeneracy pressure, which is a really, I said over and over again that there are no creative names in science and physics, or at least not very many. This one is a name that really doesn't tell you a lot about what it means. But the electron degeneracy pressure is critically important. And I want to tell you two things about it. First is that the defining thing for us is that this is the force, this is the pressure that eventually balances gravity and prevents just the complete collapse of the star. But what's important to know is that this pressure is fundamentally quantum mechanical in nature, which means that if we didn't know quantum mechanics, we would never predict this force. So the good news for you, I think, is that because it's quantum mechanical, and this is not a class in quantum mechanics, and it's not a class requiring quantum mechanics as a prerequisite, we are not going to go into very much detail about it. We will go into a little bit, but certainly at a very high level, we need to know the term electron degeneracy pressure, because this is the pressure that eventually stops this collapse again. And you need to know as well that it is fundamentally quantum mechanical. So I have to tell you a little bit more than that, though. I don't know. Many of you may be perfectly happy just memorizing the terms and regurgitating on the exam, but I want you to learn a little bit more than that. So let me tell you at least this much. So the pressure that we call electron degeneracy pressure is due to the fact that it turns out you can't cram things arbitrarily close together here. And in particular, you can't cram helium nuclei infinitely close together. And you can't push electrons infinitely close together. Just like in an atom, electrons have to occupy a specific set of states or energy levels. And that's true whether it's in an atom or if it's in the core of a star that's just finished its main sequence lifetime. So if you remember, if you ever took chemistry, some of this may be familiar, because as you fill up the electron levels in an atom, you always start at the lowest level. So hydrogen has an electron configuration of 1s, right? And then helium is 1s2, and lithium is 1s2, 2s1, and so on. If that means something to you, great. If you hate chemistry, or you never took it, or you've wiped your mind from it, then that's fine as well. But the point is that anytime that you're filling up electrons in a system, you always start at the lowest energy state and then you fill up. But you can only put one electron per state. And typically that means 2 electrons per energy level, because electrons have something called quantum mechanical spin with a value of 1/2. And we could go into and spend a whole semester on quantum mechanics, and that would be a lot of fun for me, maybe for some of you, but again, that's not what this class is. So the point is that for a low density gas, these electrons will be in a few different energy levels. There aren't very many electrons because it's a low density gas, and so they don't interact with one another very much. In a high density gas, or a gas that's known as degenerate, the story is different. In that case, you've filled up a lot of energy levels, and you don't have, and basically all of the lower energy levels are filled up, and you have very few or none in excited energy states. It turns out that when you have such a system, a high density or a degenerate electron gas, which is what we're talking about, because we're just talking about electrons here, it turns out that these resist being pushed together extremely strongly, much stronger than you would expect from any sort of a classical calculation. And just to be clear, this has nothing to do with electrostatic repulsion between electrons. It's not because the electrons are negatively charged and they repel one another. That's true, but that force is much smaller than the force due to the electron degeneracy pressure. And so the thing to remember is that once all of the energy levels are filled, if you try to squeeze them, you actually change the energy levels and force the energy levels higher. And the system really doesn't like that. And so it pushes back extremely strongly. And this results in an outward pressure that finally is strong enough to balance gravity. So we've said that once the hydrogen is completely exhausted in the stellar core, the core begins to collapse. And eventually, the only reason it doesn't collapse forever, down to a point, is that eventually the electron degeneracy pressure becomes so large that it is able to stabilize the core against further collapse. But it turns out that one of the implications of this is that as the core region, which is now we're going to refer to it as a degenerate helium core, that just is a fancy way of saying it's very dense. And it's essentially entirely helium nuclei now, because those have been formed through the fusion reactions. That degenerate helium core has gotten very small now. And it turns out that one of the implications of that, though it's far from obvious, is that the outer surface of the star actually gets much larger. So the dense helium core collapses, and the outer surface balloons out by a factor of, say, around 50. And the details depend upon the mass of the star, as with everything else. But for the sun, for example, the radius would balloon out by about a factor of 50. And so what happens then is the star gets much bigger, right? And it turns out that it turns red in the process. And for that reason, we not very creatively refer to such a star as a red giant. So if you've heard of a red giant, certainly we've referred to them in the context of the HR diagram. This is what a red giant is. It's a star that has moved off the main sequence because all of the hydrogen in the core was exhausted. And so you can see now in this sort of scaled diagram over here on the left side that now the core is really tiny compared to the rest of the star. I mean, it's always a small part of the star, but now that the outer part of the star has ballooned out to such a degree, and that at the same time the core has collapsed, it's really extremely small. And remember, the only thing that's happening, or the only place where nuclear reactions happen, are in the core region, or now, as we're going to say in the next slide, immediately outside the core. So we'll talk about that. But for this slide, I just want to emphasize how much bigger the star gets as it turns into a red giant, and how much smaller the core gets in the same process. So let's now take a look at what's happening in the new, much smaller core region. Okay, so as the helium core shrinks, as it collapses, because remember again, once the hydrogen is gone, all of the radiation pressure that was maintaining the core internally, it's gone. So now gravity wins and it starts to collapse. As it collapses, it heats up. Remember, and this is exactly the same process that led to the heating of a protostar. If you remember in the last lecture, we talked about why does a protostar shine at all? Because it's not a true star. There are no nuclear reactions powering it. So why can we see protostars? And the answer is that as it collapses, that gravitational potential energy is being converted into heat through collisions of the atoms and molecules in the star, or in the protostar rather. And then as it heats up, like anything at non-zero temperature, it radiates as a black body. So the common theme between the protostar formation and this core collapse is that you're converting gravitational potential energy into heat through that process. And so as the core collapses very quickly, as a matter of fact, it heats up, it gets hotter and hotter. Eventually it stops thanks to the electron degeneracy pressure, but now it's heated up so much that the hydrogen that's immediately outside this degenerate helium core is now hot enough itself to start undergoing nuclear fusion. So it's an interesting situation because the whole reason the collapse occurred is that all of the hydrogen fuel was exhausted, right? In the core, which is the place that it was hot enough for fusion to occur, all of the fusion that could be done was done, so the core collapsed. But by virtue of that collapse, more heat was generated, and now a layer just outside the helium core is able to begin fusing. And so that's what's depicted in this schematic. So you have at the center a degenerate helium core that's for right now just sitting there, okay, because it's hot, it's heated up a lot, first because it was in the core, and then it collapses and gets even hotter. But so far it's still just sitting there as really hot helium nuclei. But now it's surrounded by what I've labeled here a hydrogen burning shell. And by burning, as always for us, we mean nuclear fusion. So you have a relatively thin layer of fusion that is occurring just outside this degenerate helium core. And that, of course, is generating even more heat, more energy, which is further heating up that degenerate core. But the vast majority of the volume of the star is what's labeled here a cool hydrogen envelope. Now, of course, cool is relative, right? It's still star. It's still too hot for atoms and molecules to exist, so it's still a plasma. But relative to the core, certainly it's much cooler. And it's cooler than many stars. It's cooler than the sun would have been anyway as a main sequence star, right, on the surface, because it's radiating red. It's a red giant. That means that the surface is relatively cool. So now we're going to spend a little bit more time digging into this core, because if you haven't gotten the sense yet, all of the interesting stuff, that's too strong, but most of the interesting stuff, or maybe the most interesting stuff that goes on in the star is going on in the core, right? Because throughout all of the star's lifetime, the majority of the volume of the star just hangs out. Right? Fusion is always only happening in the core, or now, in this thin layer outside the helium core, and the rest of it is just kind of sitting around, hanging out, having energy sort of move through it, either through radiation or through convection, as we've talked about earlier. So let's now ask a little bit more, probe a little bit deeper on this core and this hydrogen burning shell. But before we actually go into those details, I do want to remind you of an equation that we threw up there first a few weeks ago now, and that is the luminosity relation, and how luminosity is a function of both the size of the star and the temperature. So remember, the Stefan-Boltzmann law tells us that the luminosity goes up as the fourth power of the temperature. So a very strong function of the temperature. Doubling the temperature leads to a 16-fold increase in the luminosity. And of course, luminosity goes up as 4 pi r squared, the surface area of the star as well, because if you have a larger star, there's more surface area from which to radiate, and so there's more luminosity. So this is why as the star becomes a red giant, leaves the main sequence, becomes a red giant, the surface typically will cool, right? So you go from a yellow star, such as the sun, for example, to a red giant, so that the temperature of the surface has fallen. But as I mentioned a couple of slides ago, the radius has increased quite a lot, by a factor of 50, say. And so we could crunch the numbers and say, what happens if you increase the radius by a factor of 50 and you decrease the temperature by a factor of 2, say, and it turns out that the radius wins. And so the net result is that even though the temperature has fallen, the surface temperature of the star has fallen, the luminosity has gone up quite a lot. And so for that reason, when you look at the HR diagram, red giants live up and to the right of the main sequence because they lie above the main sequence because the luminosity is higher than it is for a main sequence star of the same surface temperature. And that's exactly what we see here. So if you look at a one stellar mass or a one solar mass star again, as it leaves the main sequence, it looks a lot like the inverse of the Hayashi track. I mean, it is a little different, but it's moving up and to the right again because even though the temperature is coming down, the radius is getting so much larger that the net luminosity is going up. And so, and it moves along a track again, just like we talked about the Hayashi track as a protostar progresses towards the main sequence and becomes a star. It then sits there on the main sequence for however many billions of years it may last. But then once it exhausts the nuclear fuel in the core again, the core collapses. It begins to balloon out, not all at once. We'll often talk about it, as happening. It happens much more rapidly than anything happened in the main sequence, but it is a process by which this star now moves up and to the right on the HR diagram as it gets larger and larger. And this is not very creatively known as the red giant branch of the HR or of a star's evolution, in the HR diagram. And so just to kind of recap, in another form, sort of what's happening here, you get a smaller, more massive degenerate helium core, right? Core collapses, but now as you continue that nuclear fusion in that shell, right? So you start nuclear fusion in the shell surrounding this degenerate core, that's leading to more helium, right? Because with every nuclear reaction, you're forming helium, or with every complete set of proton-proton chain reactions. So you're constantly adding more helium and more energy to the core. So it's getting more massive and it's heating up. Because it's getting more massive, that means more stronger gravitational forces. Those stronger gravitational forces means higher pressure in this hydrogen burning shell. Okay, that increases the reaction rates, which leads to faster reactions, right? Which gives faster growth of helium in the core. And so it's a sort of sustaining set of reactions here, or processes that go here. And so as this process progresses, it speeds up. So, it begins as soon as you leave the main sequence, but then you go faster and faster along the red giant branch, and it swells, and becomes a red giant more quickly. So when the sun turns into a red giant, the diameter will be very close to 2 astronomical units, or the radius will be very nearly 1 astronomical unit. Whereas now its radius is about 0.01 astronomical units. Okay, so we quoted a factor of 50 earlier. This is a factor of 100. It's somewhere in that range, increase of the radius as it becomes a red giant. But if it didn't occur to you yet, there's a serious implication of the sun having a radius of 1 astronomical unit, because an astronomical unit, if you recall, is the average, or it's the distance between the Earth and the sun, right? And so if the radius of the sun is equal to the distance from the Earth to the sun, what that means is the Earth is sitting on the sun's surface. Okay, and essentially that's what will happen. So when the sun turns into a fully fledged red giant, it will expand to such a degree that it will completely swallow Mercury and Venus, and will just about get out to the Earth's surface. So that will be bad news for any living thing on Earth. Again, it'll become a red giant, so the temperature of the surface will fall from 5,800 Kelvin to, say, maybe 3,500 Kelvin, something like that. But as you can imagine, that's still way too hot for us. So not good for living things on Earth, but that's what'll happen. And to kind of sketch that out for you a little bit, again, it doesn't happen all at once. But today, this is kind of a somewhat to scale version. The distances are to scale. The diameters of these drawings, of these pictures here, are not to scale. But this is kind of the picture now. You get out to 7.588 billion years from now, and that's a very precise number. But you calculate it precisely, and at that point, the sun will be a red giant that will be a little less massive because it will have lost some of its mass to out into interstellar space. So it'll be about 90% as massive as it is now, and you can see that it's starting to get less comfortable here because it is growing. But you go just a little bit longer, right? You go from 7.588 billion years to 7.59 billion years. So that's only 20 million years, which is, I mean, it's a lot from our vantage point, right? But not for the sun. And now all of a sudden it's lost another 10% of its original mass. And the Earth has basically disappeared. It's gotten way too hot. And so this is kind of what the implications are of that speed up that we just talked about, how the more and more hydrogen you burn in that shell around the core, the faster and faster the process goes. And so it starts off kind of slowly, but then really, especially near the end of its life, it really picks up. And so this is all leading somewhere, as you might have gathered, because eventually what happens is that you've dumped enough heat and enough additional helium into the degenerate core that it finally does get hot enough that helium fusion can occur. So far, all of the fusion that we've talked about is fusion of hydrogen, right? Hydrogen fusing to form helium. Well, it turns out you can fuse other things too, but it has to be hotter. And I'll come back to this periodically. But if you remember several lectures ago when we first talked about nuclear fusion, the reason that it has to be hot in a star, the reason that it has to be hot for nuclear fusion to occur, is that protons are positively charged and they repel each other. And the strong nuclear force, which is responsible for the fusion processes, is only active at very short distances, on the order of a femtometer, 10 to the minus 15 meters. And so at normal temperatures that you and I are used to, if you put two protons anywhere near, you can't get them anywhere near that close to one another before they fly off, thanks to their electrostatic repulsion. The only way to get them that close is to make them really hot, okay? Because that means they're moving very, very quickly, because remember, temperature is just a measure of average kinetic energy or average speed of the particles. And so you have to get the protons really hot in order for them to be going fast enough to get close enough for the strong nuclear force to overtake themselves. Well, that effect is even more pronounced in the case of helium, trying to fuse helium, because helium has twice the charge as a proton, right? So hydrogen has a +1 charge in units of E, the magnitude of the electron charge. So, proton has a +1 charge, whereas an alpha particle or a helium nucleus has a +2 charge, right? And so it turns out that the repulsive force between helium nuclei is 4 times as large as the repulsive force between hydrogen nuclei. And so it has to be much hotter for helium to fuse than it does for hydrogen. So if you thought it had to be hot in a main sequence stellar core, it's got to be much hotter yet for helium to fuse. So that's why originally, when the core collapses, the helium, it's hot, but it's not nearly hot enough to fuse. So it just kind of sits there being hot. But eventually, you dump enough additional energy into that degenerate helium core due to the fusion occurring in that shell that it does finally become hot enough to ignite. And this is known as the helium flash. And it's known as the helium flash because it happens essentially all at once, at least on astronomical timescales. The entire degenerate helium core ignites all at once and just goes gangbusters. And so that's really a cataclysmic moment in the evolution of of the star, and it becomes the next. It begins the next stage of stellar evolution, which, as you probably aren't surprised to know, will be the next topic. But that does bring us to the end of this lecture. So I appreciate your attention. Thanks for sticking with us. And I hope you'll come back for lecture 18, where we look at, in a little more detail, at the helium flash, and then ask, well, what happens next? So until then, good evening.